Hello. In this video we're going to talk about isomorphisms a bit more. We'll connect them to some concepts we've seen previously in abstract algebra, and then we will talk about what specifically has to be the same in two groups that are isomorphic. Our outcomes for this video: we'd like to present a bunch of theorems connecting groups to previous concepts. We'll be talking about cyclic groups and so on. We'll be using facts that have to be true about groups that are isomorphic in order to determine whether or not two groups are actually isomorphic. We'll also introduce something known as Cayley's theorem and explain how it connects any finite group, or any group really, to a permutation group. Our outline will be as follows. We'll first talk about cyclic groups and what we can say about isomorphisms between them. We'll then talk about Cayley's theorem and what that means. It's a way of connecting every group to a permutation group. We'll then look specifically at properties that have to be shared between groups that are isomorphic, and we'll end with the question of how many different groups there are of a given size. Let's take a look at these three groups from our previous video. Z4, this group of elements of the complex numbers under multiplication, and the group U of 5. Now, we saw in the previous video that these were isomorphic groups. They are, each of them, groups of order 4. They're each cyclic, which you can recognize from their diagonal stripes, and they turn out to be isomorphic. You can find an isomorphism between any two of them. Now, what made that possible to find an isomorphism between them was the stripes pattern. Any cyclic group will have a Cayley table where the diagonal stripes appear if you take the rows and columns and you write them in the order in which they're generated by a generator. So for instance, in Z4, where our operation is addition modulo 4, if I take the element 1 and add it to itself, and starting with the identity, I'll take 0, 0 plus 1, 1 plus 1, 2 plus 1. That's going to sweep out the numbers 0, 1, 2, 3 in order. And when I put those as the numbers in order for my rows and columns, I end up with the stripes pattern. Now over here, the element I generates these elements in order, and in U of 5, 2 is a generator, and starting with the identity and continually multiplying by 2, we arrive at this ordering of the numbers. Now, taking that ordering for our rows and our columns gives us the stripe pattern. You can kind of see why that is. As you move down one of these diagonals, moving down a row increases the exponent in your generator along the row, but it also decreases the exponent in your generator from the column. So the net effect on the exponent is 0. The exponent stays the same, which gives us the same group element. Now, let's imagine that you were looking at any two finite cyclic groups with the same order. Now, putting the rows and columns of those two cyclic groups in order in this way, so that we see the stripes, wouldn't those two cyclic groups with the same order, having those stripes, show the exact same structure in their Cayley tables? And if you think about that generally, wouldn't that mean then that two cyclic groups with the same order have the same Cayley table structure? Wouldn't that mean that those two groups are then isomorphic? Now, furthermore, one way of finding an isomorphism is by taking these elements in the Cayley table along the columns and just mapping them to the corresponding columns in the other group. If we started with a generator of a cyclic group, wouldn't we then find an isomorphism between two cyclic groups pretty easily? Well, the answer to all these questions is yes, but let's see an example before we put a theorem up. Here we have the groups Z6 and U of 7. They're both finite groups of order 7. Here we have the integers modulo 6 under addition. Here we have the numbers less than 7 that are relatively prime to 7 and greater than 0. As you take a look at them, it's not immediately apparent that these groups would be isomorphic. The Z6 has the same diagonal stripe pattern we've seen for a long time now. U of 7 does not have that same diagonal stripe pattern, but remember, If two groups have the same patterns in their Cayley table, then we can probably show that they're isomorphic. But if two groups do not have the same patterns in their Cayley tables, that does not immediately tell us that they're not isomorphic. They still could be. So to decide whether these groups are isomorphic or not, let's take a look at whether U of 7 is cyclic. Now, as you take the elements of U of 7 and you look at what happens when you repeatedly multiply them, you'll see pretty early on that 3 times itself gives us 2, 3 times 2 gives us 6, 3 times 6 gives us 4, and so on. And if you were to write out all the elements you arrive at, all the elements you generate, you'll eventually sweep out all of the elements in the group. Therefore, U of 7 is cyclic and 3 is a generator. Now, if we were to take this order that the elements appear in, and if I were to use that order along the rows and the columns of U of 7, I would see something happen in the Cayley table. Let's see what it does. You'll notice that at this point we end up with these diagonal stripes. All right. With that in mind, it seems apparent that Z6 and U of 7 are isomorphic. In fact, we can just take the order that these things appear in their rows, and just map the corresponding elements to each other. So 0 will map to 1, 1 will map to 3, 2 will map to 2, and so on. More generally, you'll see that because these elements were ordered by multiplying by 3, we have a nice expression for our isomorphism. We can say that the map phi from Z6 to U7 can be given by just taking that integer from Z6 and taking 3 raised to that in the group of U7. Alright, now putting this all together, because we can take any two cyclic groups of the same order and kind of order their columns in such a way that those stripes will appear and the Cayley tables will be the same, any two finite cyclic groups having the same order will be isomorphic to each other. That's because you can show that they're isomorphic to Zn. You can use a map very similar to the one we just talked about for U of 7. Just take 1 in Zn and map that to a generator of the finite cyclic group. And then because you can get an isomorphism from Zn to any other cyclic group of order n, and isomorphism is gives us an equivalence relation, that means that any two finite cyclic groups of order n will be isomorphic to each other as well. A similar thing happens with infinite cyclic groups. We can map 1 to a generator of the infinite cyclic group, and we'll see that the integers as a group is isomorphic to that infinite cyclic group. So in a sense, for every number n, there is exactly one different cyclic group of order n. Any two cyclic groups with that order are isomorphic to each other, so there really is just one cyclic group if we're just talking about groups that are structurally the same. So with that, we'll move on from talking about cyclic groups and start talking about Cayley's theorem. Now, to preface Cayley's theorem, let's talk a little bit about permutation groups. For our purposes, a permutation group is any group whose elements are permutations, and the operation of the group is composition of permutations. So the symmetric group with n elements is certainly a permutation group, but we can also get a permutation group by taking just a subset of permutations and putting them together, and if they form a group, then we'll call it a permutation group. Well, in addition to talking about the symmetric group, let's take a look in this example at the dihedral group. You'll remember that D3 consisted of the symmetries of an equilateral triangle. We listed them in earlier discussions. There are 6 such symmetries, 3 rotations, and 3 reflections. We'll say that the reflections are along these axes indicated in the picture there. Now, one interesting connection between the dihedral group and the symmetric group comes from numbering the corners that your vertices of the triangle occupy to begin with. If we start by imagining each of these symmetries as sort of a permutation coming from taking a corner in a vertex in one corner and sending it to another corner, then there's a very natural correspondence between these elements. a rotation of 120 degrees, for instance, is going to take the corner in, the vertex in corner 1 and send it to corner 2, the vertex in corner 2 and send it to corner 3, and the vertex in corner 3 and send it to corner 1. So 1 maps to 2, 2 maps to 3, 3 maps to 1. That's exactly this permutation there. R240 sends things the other way around, and that agrees with this permutation here. The permutation, or the symmetry F, would exchange the vertices lying in corners 1 and 2 while keeping the vertex in corner 3 the same. And so F corresponds very naturally to this permutation 1, 2. With that in mind, it's pretty easy to check and to verify that these two groups are isomorphic. D3 is isomorphic to S3. Now, as another example, remember we said that any two finite cyclic groups with the same order are isomorphic to each other. So if I were to take the subgroup generated by 1, 2, 3, 4, 5, this permutation has order 6, and if I take the subgroup generated by it, I'll get a cyclic group of order 6, which we just got done saying should be isomorphic to Z6. Now in both of these cases, I've taken a group that I'm familiar with, and I have shown a permutation group that it is isomorphic to. This turns out not to be a fluke. Cayley's theorem is an important theorem. It states that every group is isomorphic to a group of permutations. Now, how do we prove this? Well, the idea of the proof is to take a look at the Cayley table of G and use the rows of the Cayley table to come up with permutations in our group of permutations. Specifically, what I'm going to do is list my elements of my group. In this case, I'm talking about U of 12. I'm listing those elements across the top of my array, and then I'm going to take each row of the Cayley table and put it as the bottom row in one of these permutations. Now, the amazing thing about this is that these permutations form a group. You can do a little work yourself to try it out. And this correspondence, taking each element and mapping it to the permutation that uses its row of the Cayley table, that is a group isomorphism. Now, I would encourage you to prove this. We won't go through the proof details here, but think about how you would do this. Now, that is Cayley's theorem. It's an important theorem. Please remember it. Every group is isomorphic to a group of permutations. We're not saying that it's isomorphic to the full symmetric group of permutations. We're just saying that there is a collection of permutations out there that form a group isomorphic to the group that we are interested in. All right, we'll now talk about properties that are shared by groups that are isomorphic. At this point, we've gone ahead and shown that lots of things are isomorphic to other things, and so you might be excused in wondering whether it isn't true that every two groups are isomorphic, if they've got the same order, maybe. Let's take a look at these two groups. Again, we've got some groups of order 4. This group on the left is the group of symmetries of a rectangle which is not a square, where the H and V refer to reflections along the axes indicated there, and R180 refers to a 180-degree rotation about the center of the rectangle. Now, with these two groups having 4 elements, are they isomorphic? Is it possible that if we were to reorder the rows and columns of this group, we might see the same diagonal stripe pattern that we see in the cyclic group? Well, let's take a look at a few properties that have to be true for any two groups that are isomorphic. Here's a long list of properties that must be shared between groups that are isomorphic. We'll see another slide talking about even more in just a second. But supposing that phi is an isomorphism from a group G onto a group J, so we're supposing that G and J are isomorphic and that there is an isomorphism phi going from G to J, it must be the case that the identity of G is mapped to the identity of J. That specific element has to be sent to the specific element if we're talking about an isomorphism. Also, if A and B commute in G, then phi of A and phi of B are going to commute in J, and vice versa. Now, one thing you can notice is that these are properties that you can recognize by looking at the Cayley table. Looking at the Cayley table, we're going to be able to see what the identity of the group is. Looking at the elements A and B in the Cayley table, we're going to be able to tell whether they commute or not. And in general, anything you can get from the Cayley table should be the same in both groups. Moving on in our list here, for all A and G, and for every integer, positive, negative, or 0, the nth power of A needs to be mapped to the nth power of phi of A. This follows from the operation preserving property of the isomorphism. A group G is cyclic and generated by A if and only if J is generated by the image of A under the isomorphism. It turns out that A and its image have to have the same order no matter which element you're talking about. If G is finite, then G and J have exactly the same number of elements of every order. They have the same number of elements of order 2, they have the same number of elements of order 3, and so on. And then finally, for a fixed integer k and a fixed group element b, the equation x to the k equals b will have the same number of solutions, the same number of elements making that true in G, as does the same equation x to the k is equal to phi of b in J. Alright, so let's take a look at this long list of properties that must be true for isomorphic groups and see if they can help us decide whether the groups we were looking at a minute ago are isomorphic or not. One thing we'll pay attention to starting out, one thing that's a good thing to check, is this property number 6. If two groups are isomorphic, then they have to have exactly the same number of elements of every order. So in particular, if we were to take a look at these two groups, we might start with the smallest order that's not 1. We'll take a look at the elements of order 2. Now an element of order 2 is one where when you times it by itself, you get back the identity. In this case here, this group has R0 as the identity, and as I take a look at R180 and H and V, they all have order 2, because putting any one of them together with itself creates the identity. So I have 3 elements of order 2. Remember that the identity has order 1. Now in Z4, as I look at the elements, 0 is the identity, and as I look on that main diagonal, I see that only 2 has order 2. There's only one element of order 2, and there were 3 elements of order 2 over in this first group. So that tells us that the two groups are not isomorphic. If they were isomorphic, you would expect to see the same number of elements of order 2 in both groups. Furthermore, one thing that will stand out to us is that Z4 is cyclic. It has an element of order 4, and this group is not cyclic. It doesn't have any elements of order 4. This idea of being cyclic or not is important, and it shows up in our next theorem. So here's our second list of properties that should be the same in groups that are isomorphic. Supposing that phi is an isomorphism from a group G to a group J, your group G will be abelian if and only if J is abelian. If two groups are isomorphic, they're either both abelian or they're both not abelian. Statement 3 is the statement that they are either both cyclic or neither one of them is cyclic. And statement 2 says that the center of G corresponds to the center of J. If you were to take the elements of the center of G and look at their images in J, what you will get is exactly the center of J. Okay, statement 4 says if K is a subgroup of G, then the image of those elements forms a subgroup of J. Now, an isomorphism has an inverse, and this statement 5 says that the inverse function, phi inverse, is an isomorphism from J onto G. Finally, if K prime is a subgroup of J, then the pre-image of K prime is a subgroup of G. This tells us that the subgroups behave very much the same in both G and J, and this list of properties and the one on the previous slide are very helpful to us in deciding that two groups are not isomorphic. We know that if one of these properties does not hold for our pair of groups, then that must mean that the two groups were not isomorphic, that there was no isomorphism between them. Well, now it's time for an exercise for you. Shown here are the Cayley tables of 3 groups. Are any 2 of these isomorphic? If so, the challenge is to find an isomorphism between them, saying which element maps to which, and if not, you need to point to something specific that tells you that they're not isomorphic. Go ahead and pause the video right now if you like and try to answer this question. All right, I'm going to suppose that you've gone ahead and tried for yourself to see which of these groups, if any, are isomorphic. One thing we'll do as we take a look at this is notice first the orders of the elements. As you take a look at the identity in each of these groups, you'll see that A is the identity here, and there's just one element of order 2. In this group, U is the identity, and then there's just one element of order 2 on that main diagonal. And then in this group, 1 is the identity, and whoa, there are 3 elements of order 2, it turns out. Okay, since isomorphic groups have to have the same number of elements of each order, and this group has more elements of order 2 than the others, it's certainly not adjacent to either of the other 2. All right, so we have not decided whether the first 2 groups are isomorphic. As you take a look at their Cayley tables, you'll see that this one does have that nice diagonal stripes pattern. It looks to be a cyclic group. This group does not have exactly that same diagonal stripe pattern. We see in this diagonal, for instance, the B in the middle doesn't match the E's on either side of it. So the Cayley tables don't match exactly. But remember, this does not necessarily rule out that these could be isomorphic. We've got to look a little bit deeper. Now, as we take a look at these groups, we do know that this group is a cyclic group because of that pattern we see. We also know that any 2 cyclic groups with the same order will be isomorphic. So if I can show that this group is cyclic, I'll know that it's isomorphic to the second group there. So let's start taking a look at the subgroups generated by each of the elements in this group. We don't have to look long before we find out that the element E generates the entire group. And so this is a cyclic group. And because it's cyclic and this is cyclic and they have the same order, our theorem from the beginning of the video tells us that these 2 groups are in fact isomorphic. In fact, if we want to find an isomorphism, we know that we can just take the elements in their cyclic orders. So V generates this group, and this is the order it generates the elements in. We know that E generates this group, and E generates the elements in this order. And so that tells us that the elements in this order should correspond to the elements of that. One isomorphism we can come up with is that A maps to U, E maps to V, C maps to W, D maps to X, B maps to Y, and F maps to Z. All right, so this concludes our discussion of our properties that are shared by isomorphic groups for now. To end the video, I'd like to talk about this question of how many different groups there are. Now, in one sense, there should be infinitely many groups of any given order. I've gone ahead and listed here a few groups we've seen so far that all have order 4. Now, there's nothing to stop me from just changing the names of these elements, calling them something different, and then claiming that I've got a different group of order 4. But what I'm interested in particular is not whether the names are different, but whether the structure is different. How many different groups are there if I'm going to treat groups that are isomorphic as the same group? For instance, we know that these 3 groups are isomorphic. I'm just going to call that one group. This group is not isomorphic to those, so here's a second kind of group. Now, is it true that these groups fit into one of those collections, or are they really different from any of those? How many non-isomorphic groups of order 4 are there? Well, this is not a trivial question as you look at different orders. In fact, there's a whole article on finite groups that's interesting. This appears on Wolfram Math World, kind of an encyclopedia for mathematics, and I would encourage you to take a look at that. You'll see as you navigate to that article that the article for finite group, as we scroll down a little bit, has a table. And in this table we see a list of all the groups of certain orders. So in this table, H stands for the order of the group, and we have a list of all the abelian and the non-abelian groups of that order. Now as we look at groups of order 4, The table tells us that there are 2 abelian groups of order 4 and 0 non-abelian groups of order 4. So that gives us a grand total of 2 groups. Now, going back to our question here, there are only 2 groups of order 4. That means that each of these groups must belong to one of those isomorphism class. Now you'll find in the Math World article that the 2 groups of order 4 were named C4 and C2 cross C2. I'll point out to you that Math World uses Cn to stand for the cyclic group of order n. We've been using Zn. It's the same group. They're isomorphic. We will see later what the times means, but that does mean that if Math World's list is correct, and as far as I know it is, each of these groups should be isomorphic either to the cyclic group of order n or to this mysterious group C2 cross C2. Well, deciding how many groups there are, how many different groups there are of a particular order, will be one of the things we'll come back to multiple times through the rest of the semester. It's kind of an interesting question to decide exactly which groups are there, how many different groups there are, and what is the structure that you see among the groups that you find. Well, that concludes our tour through these properties of group isomorphisms. We've talked about Cayley's theorem and connections to permutation groups. We've talked about what has to be true among groups that are isomorphic. We've talked about cyclic groups and how there's basically one cyclic group of any particular order. And we've ended with what is to us a bit of a research question. How do we know how many groups there are of a particular order? How do we narrow it down and figure out just how many or how few groups there are? We'll find out as we go along.